Okay, so thanks a lot. So welcome to this second session about these reaction diffusion equations coming out of chemical networks. And maybe just to summarize what we did yesterday, let me write down a somewhat more precise version of the theorem that I just wrote down at the end of the lecture of yesterday. And actually, let me quote a few more persons because the version of the theorem that I will now write down is a sort of mixture of various results obtained in different papers. So one of the papers was written together with José Alfredo Canizo and Clemens Fellner. There is a paper from another group by Thierry Goudon and Alexis Vasseur. So this is a group based in Austin. Then there is a more recent paper written also with Bao Kwok Tang, who is in Graz in Austria with Clemens Fellner. And then there is the last paper, which I quoted yesterday, which was written I think almost 10 years ago, together with Michel Pierre and Julien Vauvel. So this is a group based at that time in Rennes. Okay, so let's take omega an open bounded smooth subset of Rn. Let's take, let's say, diffusion rates di, which are strictly positive. And let's take data, initial data, which live in L2 of omega. Then, so for the first example, what we can say is the following. There exists a weak solution. So to be more precise, this solution lives in L2 of 0t times omega for all strictly positive t. So this is a global weak solution. But the L2 norm may grow with t to the system which corresponds to the example 1 that was written yesterday. That is dt ai minus di Laplacian ai is equal to minus 1 to the I a1, a3 minus a2, a4. And as you can see, since the weak solution is in L2, all terms are defined. Here you can do the product and get something in L1. And here you can take derivatives in the sense of distributions and get something which makes sense. Okay? So this is an equality in the sense of distributions, and more precisely with test functions which take into account the boundary and initial condition, which I now write down. So the homogeneous Neumann boundary condition and the initial condition which corresponds to the initial datum in L2. So this is what I wrote down yesterday, almost exactly. And now I want to add the fact that if the dimension is small enough, so in that case, it is less than 2, so in dimension 1 and 2, and the initial data are smooth enough, so let's say C infinity, but it really depends on what you want to get as a conclusion. So if you want C infinity in the conclusion, you put C infinity, of course, in the initial datum. Then the solution defined above is classical and belongs to the infinity of 0t times omega bar for all t. So if you prefer, it is in this space. And finally, it is unique among strong solutions at least, but most probably also among weak solutions. So let me not define extremely precisely what is a uniqueness result here, but at least it contains the fact that two strong solutions with the same data are equal. Okay? And finally, for all strictly positive p, so let's say integer, if you look at the CP norm on 0t times omega bar, this is something which is bounded by a constant which grows at most polynomially with capital T. Let's write it this way. This is bounded by a polynomial. So this plays a role at the very end, when we will see at the very end of the last talk of this lecture, that this is something which helps when you want to get a complete theory for this system. So that is for the first system, for the first example. And for the second example, so you keep the same data. This time, instead of having 4 diffusion rates, you have only 3. The same for the initial data. And you can say exactly the same. That is, there exists a weak solution in L2 for all. So I will not write it again. So there exists a weak solution in L2 for all t strictly positive to the system, which is now dt A1 minus D1 Laplacian A1 is equal to minus A1 plus A2 square. dt A2 minus D2 Laplacian A2 is minus 2 A2 square plus A2 A3 plus A1. dt A3 minus D3 Laplacian A3 is equal to A1 minus A2 A3 plus Neumann boundary condition initial data, what is written here. And moreover, now for this system here, it's possible to go up to dimension 5. And then all the rest is the same. Okay. So sorry for my laziness. I do not write down. It's exactly the same sentence. Okay. So the main difference between the two cases is that actually in the case where the situation is much better in terms of estimates for the various terms in the right-hand side. And because of this, it's possible to go much further in terms of dimension. We will see in a brief moment why this makes sense. So this is a sort of summary of what we discussed yesterday. Let me briefly recall how the proof is obtained of those results. The first thing we said is that it's possible to consider a sort of approximated system for those two things. So we consider, so I will write only the first example. The other one being exactly identical. the approximated system in which you take the same left-hand side, but for the right-hand side, you take the reaction term, which has a quadratic growth, and you divide it in such a way that when both quantities are large, then you sort of saturate this growth. So the way to do that are many possible ways, but one which works very well consists in just adding here the square of all the concentrations, and you put in front 1 over n in such a way that when n goes to infinity, you recover the original system, okay? So the point of doing this is that when you have a reaction diffusion system with a smooth unbounded right-hand side, you have general theorems, which are actually not very difficult to prove, which tell you that you have existence and uniqueness of a smooth solution to the system, okay? So here by general theorems, so if you're interested, you can look, for example, at the book of Ledichenskaya and Uraltseva. If you have not done it, it's worth trying anyway. So by general theorems, let's say, such an AIN exists. Of course, plus Neumann boundary condition plus initial data, okay, which are exactly the same as for the. And then you try to get the a priori estimates that you computed on the limiting system. You try to check that they are indeed also satisfied by the approximated system and that the constants are independent on n. So this is actually very easy in the case of this system here, because this thing here is really not a problem when you're trying to, for example, get something out of the duality lemma. So by duality lemma, so this is what we saw yesterday. We know that this quantity is bounded by Ct, and actually Ct here, if you remember, it's something which depends on the initial datum, and it grows at worst like square root of t. So it's really a polynomial growth at worst. So once you know this, you have almost finished, in the sense that if you want to pass to the limit in this equation, well, for the left-hand side, there is no problem at all, because you can just pass to the limit in the sense of distributions. You know that AIN is bounded in L2, so you can extract a subsequence which converges towards something. So let's say like this. And you already know that this term will behave nicely. And then you just have now to check that you can pass to the limit here. So this term is no problem at all. The whole point is to pass to the limit in the products that you have here. And so for this, you basically need two things. The first thing is that you have to extract some strong compactness in both t and x in order to pass to the limit almost everywhere. And this, in that case, is very easy because you see that this quantity here, since it is equal to this, it is bounded in L1 because this is bounded in L2. So since you know that this quantity is bounded in L1 of 0t times omega, you use the fact that the heat equation transform you the reciprocal of the heat kernel, if you will, or the heat kernel, if you will, transforms L1 in any bounded set of L1 in a compact set of LP for some P which is strictly bigger than 1. And you get that AIN is converging almost everywhere towards AI. So you get the first thing that you need in order to pass to the limit. The last one being that you need both quantities to be equi-integrable. You need some extra integrability, if you wish, to pass to the limit in L1. So in order to get that this quantity goes, for example, towards A1, A3 in L1, you need some extra integrability. Okay. And this is the only thing which is lacking. So let me now proceed as if we knew that it works, that this extra integrability exists. And let me show that if you are in the good situation, that is, if the dimension is small enough, then actually there are extra estimates which will give you this extra integrability, so that we can come back at the very end to the case when n is large and check if we can have the extra integrability. Okay? So let's do first this part of the proof before coming back to the case when n is strictly bigger than 2. So, yeah. Mm-hmm. So if you have something which is quadratic, which is general but quadratic, yeah, then basically everything will work well as long as you can use the duality lemma, which means typically that you have some conserved quantities, let's say.
What's my question? So somehow, I mean, the fact that it works, I mean, you rely on having at least one conserved quantity.
Yes, so more precisely, if you want to use it, you need that you have a certain number of conserved quantities, but it can be only one, but provided that all the concentrations enter inside.
Yeah, okay. So somehow
you need that all species be concerned by the conserved quantity in some sense. Okay, so let me now turn to the case of small dimensions. The case when n is equal to 2 is very specific. This is actually a sort of critical case for this equation, and I will not treat it because it needs, I will say a few words at the end to explain how it works. But let me do in detail the case when n equals 1, in which it's really easy to get the result. So this is a case n equals 1, and this is the first example, okay? So what we shall use is actually the properties of the heat kernel, and the property that you have to have in mind is that the heat kernel transforms LP in LQ with a Q which can be computed in an optimal way. And so what I will write down is can be found in any good book on the heat kernel. But I will say a few more words about it because we need something, some extra information which sometimes is not so easy to find in the books. So suppose that omega is a good set. that is like we said here. And take V in LP of 0t times omega. And suppose that for some capital D strictly positive, dtu minus d Laplacian u is dominated by V, and that u is positive, or u has no sign, but this is equal to V. So usually you have two possible settings. And that you have Neumann boundary condition and also u at time 0 lives in LP of omega. So you take the same P for the initial datum and the source. Then it's possible to say that you can bound u in LQ by a constant times, so u at time 0 in LP plus V in LP of 0t times omega. Like this. And the link between Q and P is that, so 1 over Q has to be strictly bigger than 1 over P plus 1 over 1 plus 2 over N minus 1. And here, N is a dimension. So when N is equal to 1, this is just 1 divided by 3. So here you have exactly minus 2/3 when you look at this term here. And so this is when this quantity is positive. So this is for P less than 1 plus N over 2. And Q is equal to infinity if P is strictly bigger than 1 plus N over 2. And if P is equal to 1 plus N over 2, you get all LQ except L infinity. Okay. Sorry? Yeah, exactly. You get, you get the critical case is, so the situation is the following, that if the dimension is large, you see that here you get something which is very close to 1. And so you have here 1 minus 1 is equal to 0. So you get something which is minus a very small number. And so the Q that you get is very close to P. So in large dimension, what it tells you is that the heat kernel gives you some extra integrability, but it's very, very small. Okay? It's just a little better than the integrability of the right-hand side. But when the dimension is small, and for example, in dimension 1, this is striking, here you will get, as I said, 1/3. So here you get minus 2/3. And so Q is usually much bigger than P. And actually, you will get infinity as soon as you are in, if I'm not mistaken, in L3½ plus epsilon. So if you start from some P here, which is 3½ plus epsilon, you immediately get to L infinity. Okay? So this is a point in which, of course, the dimension is very important. And it's the reason why you have good results of smoothness when the dimension is small. This is very close to using Sobolev embeddings anyway. So. Yeah, sure. So it's really possible, of course, to have a much more detailed smoothness estimates. Exactly. But if you think of the way the equations are written, with these nonlinearities in the right-hand side, actually what you need is the same P for T and X. So it's the reason why we systematically use this, because yes, let's say divergent exponents for T and X are actually not really usable for this type of nonlinearities at the end. So let me explain now very briefly, using this proposition, how it's possible to do the case when n is equal to 1. So you can look at the final equation or at the approximated equation. It doesn't change anything. The point is the following. If you know that AI is in L2, then using the multiplication, you will get that A1, A3, and A2, A4 lie in L1, okay? And then you use the heat equation, you use this proposition here in order to deduce that AI lies in LQ. And what is Q now? In order to get Q, you replace P here by 1 and N by 1. So as you can see, you get exactly 1 over 1 plus 2, so 1 over 3, which means that Q is any number less than 3. So what you get is actually that AI is in this space here, which I will call L3 minus 0, which means any LP for P less than 3. And then, as you can see, you improved the integrability of the AI, so you can bootstrap this. And now you get that. It's a pity I have to change, but okay, let me do it here. So we know that now A2, A3, and A1, A3, and A2, A4 lie in L3 half minus 0. And then you can use now the proposition, but with P equal to 3 half instead of 1. And so if you put here P equal to 3 half, you get 2/3 minus 1, so it's minus 1/3, plus 1/3. So you get exactly 0, and this is a critical case in which you know that you will get in any LQ except L infinity. So this tells you that now AI lie in L infinity minus 0 with the usual notation. And you need yet an extra iteration. So this tells you that A1, A3, and A2, A4 now lie in the same space. And now, of course, this will give you that AI is in L infinity. So once you are at this level, you know that the right-hand side of the equation is bounded, and you can use the general theorems in order to get the C infinity character of AI. This, of course, needs that the initial data are in the same space. Okay? So if you look at what I have written at this level, you can see that I have proven exactly this, well, for n equal 1, not for n equal 2, up to now at least. And the only thing which is lacking is the fact that the constants are polynomially growing. So actually, this comes from the fact that in the proposition here, the CT, which is here, is also polynomially growing. And this is not so easy to find in the books. but one can really do it by hand and check it. Actually, this is very easy if you are looking at the whole space. If you are in a domain with Neumann boundary conditions, you have to do it by yourself, and it takes some time, but it's true. So by using those polynomial growth a certain number of times, but a finite number of times, you still get a polynomial growth at the end, and this concludes, let's say, the proof of the theorem in the case of the first example with n equal to 1. Now I would like to show you the second example in the case when n is equal to 2. The reason for that is that this, I think, will make clear why the situation is much better for this one, actually, with respect to the other one, and so why you can get up to 5. But I will not prove it for n equals 5 because it needs, like, I don't know, maybe 15 iterations or a large number of iterations. But with n equal 2, it's reasonable. Yeah, so let's clear the theorem. So for the second example, and n equal 2. Of course, we will use the same proposition, but the way we start is the following. So here we will make use of the asymmetry between the various AI. Since the right-hand sides are different, we can use, let's say, the best one in some sense in order to get the best possible result, and in this way we can try to minimize the number of iterations. So if you look at the right-hand side here, what you can see is that since in the proposition you use this variant in which you just need a bound from above, you can in some sense discard all what is negative here. So this term, and this term will play no role in the smoothness estimate. So you just keep this one, this one, this one, and this one. Then when you do that, you see that the third equation is really the best one because the positive term is as a linear growth, whereas in the two other ones, you have a quadratic growth in the positive term. So the idea is first to use the third one, and we know a priori that A1 is in L2 by the duality lemma, and so we will get something on A3 that we cannot get immediately for the two other species. So let me write things in this way. We know that A1 is lying in L2 thanks to the duality lemma. And then we use a proposition. Now we are in dimension 2, and we start from p equal 2. So we have here p equal 2, and here n equal 2. So this gives you 1. 1 minus 1 gives you 0. And, sorry, this is 2 divided by 2, so you get 1 here. So here you get 1/2. And here you also get 1/2. So you get 1/2 plus 1/2 minus 1. So you get exactly 0, which is the case which I did not write down, in which you get LP for any p except L infinity. So what you get is actually that A3 lies in L infinity minus 0 of 0t times omega. And now you can use this information in the second one, because in the second one, you can see that you don't take this term into account. And those two terms now, this one, you know that it is in L2. And this one is a product of something which is known to be in L2 by something which is known to be in L infinity minus 0. So all of it is in L2 minus 0. Okay? So let's say this implies that A2, A3 plus A1 lies in L infinity minus 0. Thanks to the fact that A1 and A2 are both, so A1 we already know, but let's say A2 is also in L2. Do you agree, or? Sorry, 2 minus 0. Okay, so I use now the, actually exactly the same estimate as previously. The fact that we have 2 minus 0 instead of 2 doesn't change anything, because anyway, there is a strictly bigger in the inequality. So what we get in this way is that A2 lies actually in L infinity minus 0. So like this. And once we know that, then the first term here is in L infinity minus 0. Okay? So this ensures that A1 is in L infinity. And as you can see, we have done the whole process in order to get from L2 to L infinity for A1. But once we know this for A1, we can iterate. We now know that A1 is L infinity, so A3 will be also in L infinity. And once we know that both A1 and A3 are in L infinity, since A2 is in L infinity minus 0, this term here is in L infinity minus 0, and we deduce that A2 is in L infinity. Okay? Of course, here the details are not really important. So from all of this, we deduce that the AI are finally in C infinity, like here. And the whole point here is not to really look at the details of the proof, but to keep in mind that the fact that in some of the equations you have the positive term which has a growth which is less than in some other equation means that you can try to do things iteratively, not for all equations at the same time, but first for one equation, and then you can go to the other one, and then another one, and so there is a sort of general principle for these models, which is that when you have an asymmetric situation, it's always much better than when the situation is completely symmetric. Because when it's completely symmetric, you don't know from where to start, basically. So here you have a good starting point. If you try to push these ideas, you can see that it works up to n equal to 5. So for n equal to 5, as you can see, I have already like, I don't know, 6 times I used the proposition. So for n equal to 5, you use it like I say at least 15 times, but maybe more actually. But anyway, it gives you the results at the end. Well, so with respect to the theorem I wrote down, if you remember, there was a question of, let's say, equi-integrability or extra integrability for the quadratic terms, for the products here, which was still pending. Those computations actually solve this problem in the case when the dimension is small enough. But we want to have it for any dimension. And at this point, it is useful to use something which I did not write down yet, and in fact, which is at the heart of the structure of the equations that we wrote down. It is the fact that you have an entropy structure for those equations. And this entropy structure, it comes from the fact that in the first case, we have a detailed balance, which I will define a little later. And in the second example, we have, let's say, a weaker notion of balance. This is called complex balance equilibrium, which still entails that there is an entropy structure. So let me now explain the entropy structure for the two systems. And it will be the key of this extra integrability that we need in order to finish the theorem. So I will do something which is normally forbidden in books. That is, change the chapter before the theorem is proven. But anyway, let's do it. So for the first one, in order to understand the entropy structure, let's first try to check what are the equilibria. Okay? So in the first example, let's look at the equilibria. And to be more precise, let's look at the homogeneous equilibria, the one which do not depend on x. Okay? So the equation is not written anymore, but I think you can still see it here. You see that in order to be an equilibria, you just need this quantity to be equal to 0. Okay? So let's call those equilibrias ai infinity for I equal 1 to 4. You see that the condition to be an equilibrium is this one. Okay? And what will fix the equilibrium is the fact that it also satisfies the constraints coming from the conservation laws. If you remember, we had 3 conservation laws for this equation, and this can be written in this way. So, if you remember the names we gave yesterday, we wrote it with 3 letters, which were M1, M2, and M3. So those quantities are non-negative. And to be completely precise, those quantities were the integral over omega of this. And so this is strictly true when omega is of Lebesgue measure 1, okay? Which I will always suppose. So the equilibria for the first example are given by this set of equations, and it is easy to check that there is a unique solution to these equations, which actually can be written down explicitly. It's not very difficult, provided that all the ai infinity are non-negative. Okay. So there is a unique solution ai infinity which is non-negative. For, let's say, pedagogical purposes, it will be easy to compute in the case when all the mi are equal to 2, and then it's clear that this solution is just ai infinity is equal to 1 for all I. And I will use this case in order to do the computations tomorrow. So this is for the first example, okay? Now let's look at the second example. That's perfect because it's written here. If you look at the equilibria for the second example, you can see that what you need is exactly that those quantities are equal to 0, like this. And you have to remember that you have one conservation, which is 2a1 infinity plus a2 infinity plus a3 infinity equal to 0. Sorry, to m. Thanks. which is non-negative. And so it's still possible to compute all of this, because basically it's just quadratic equations. And one can check the following. It is that there exists a unique solution which is strictly positive for all I, provided that the M is strictly positive. But the important thing here, and this is completely different from what happens here, is that there is also the possibility, in that case, to have an equilibrium in which both A1 infinity and A2 infinity are equal to 0, but A3 infinity is different from 0. And the reason for this, if you look at the equations, is just that A infinity in the three equations always appears with A2 infinity in front. And so when A2 infinity is equal to 0, then A3 infinity disappears from the equation. And so there is also one solution of the form 0, 0, A3 infinity. And to be precise, of course, this is M. Okay. And this described all solutions, such that A infinity, AI infinity is non-negative. So actually, you have, in this case, you have something which is rather different from what you have here. That is here, in some sense, there is a unique equilibrium provided that non-negativity is imposed. Here you have two different equilibria, one which is called sometimes interior because all the AI infinity are strictly positive, and one which is called sometimes boundary equilibrium because it is on the boundary of the set which is given by this, okay? So let me introduce this vocabulary. So this is a boundary equilibrium. And this is an interior equilibrium. Let me say immediately that if you look from the point of view of ODEs, it's very easy to show that this equilibrium here, the boundary equilibrium, is actually unstable. So this one is unstable for ODEs. Let's say linearly unstable. Whereas this one and the unique equilibrium here are stable for the ODEs. So this is linearly stable for ODEs. And here, this one is also linearly stable for ODEs. So I do not perform the computations of all this, but really it's just solving second-degree equations and checking elementary linear algebra. So there is really no difficulty at this level. Mm-hmm. Sorry? So no, we will show that there are no limit cycles, but we will show that. I mean, it's not that. I think they are, because I mean you could not turn around because you're on the boundary for the bad one, and for the other ones I'm not completely sure. So I will not completely sure if you have stable or well, no, I have not in mind the. Sorry, did I want to say something else on this? Yeah, so yeah, the last thing I wanted to say is that once again here I will, mostly tomorrow, use the case in which m is equal to 4, because in that case it's easy to see that taking ai infinity equal to 1 gives the interior equilibrium. Then ai infinity is equal to 1 for I equal 1 to 3 is the interior equilibrium. And in the same case, of course, 0, 0, 4 is the boundary equilibrium. Okay, so in that case, everything can be written very quickly. Okay, so the fact that you have only one interior equilibrium, of course, leads you to think that there is maybe a Lyapunov functional which will drive you towards this equilibrium. So this is one way of explaining why you have to look for Lyapunov functionals. But there are various other reasons. From the point of view of people who have a kinetic background, there is the fact that those equations can be, at least the first example, it can be shown to be a limit of a Boltzmann equation for mixtures for which we have the H theorem. So we know that by passing to the limit, we should get another Lyapunov functional, which is what remains of the H functional at the Boltzmann level. So that's the second reason. And then there is, I would say, a more physical reason, which is that for reversible chemistry, we know from traditional thermodynamics that we have an entropy or a free energy or a free enthalpy, etc., which comes really from the books, let's say. So anyway, the point is, in the setting that we have chosen here with those easy examples, this Lyapunov functional is naturally the integral of the ai log ai summed over all possible I. And since I prefer to have things which are non-negative, I will write instead ai log ai minus ai plus 1 in order to have systematically a Lyapunov functional which is non-negative. Okay? So let me now prove that this is indeed a Lyapunov functional. So I will do it for both examples, because actually the computation, I think, it's interesting to see the difference in the computation for the two examples which have, and this will show the different nature of those two examples, I think. So I will use the following notations now. So let's define H of A1, A2, A3, A4 as the sum from 1 to 4 of AI log I, AI minus AI plus 1, okay, which is positive. Okay, this is a positive function. And let's call the same for, but with a capital H, for the integral over omega of the same quantity. Okay? So this is in some sense a local entropy, and this is a global entropy for the systems. And the same, I will use the same notations for the second example, except that you have only 3 variables inside. Okay? Or A1, A3 for the second example. Sorry?
So the equilibrium you're choosing here are all the same AI?
Yes, so that is what happens in the spatial case when you take m equal 4 or m equal 2, in which you get 1. But Anyway, here, this will be true whatever the equilibria are, and then I would sort of look at the relative entropy. But of course, you're right. I mean, those examples are chosen in such a way that what you will remove is 0. So, yeah. Well, anyway, let me now do the computation for the first example. So if I compute the derivative of capital H, then this is exactly the integral over omega of the derivative in time of this quantity. The derivative of this quantity is just the logarithm of I, like this. I must not forget the sum, like this, times dTAI, okay? And dTAI is just minus 1 to the I times A1, A3 minus A2, A4. And then I have to take into account the Laplacian. So this is the, let's say, the part which is due to the reaction. And then the part which is due to the diffusion is just logarithm of AI times Laplacian of AI, and I must not forget the diffusion term, the diffusion rate di in front. Okay? You agree with this? So then, the computation is extremely simple because here it's exactly the same computation as in Boltzmann's operator. That is, you have, this is log A1, log A2 plus log A4 minus log A1 minus log A3, which you can rewrite as log of A2, A4 minus log of A1, A3, okay? So this is equal to minus log A1, A3 minus log A2, A4 times A1, A3 minus A2, A4, which is the usual term that you have in the Boltzmann equation. And this is clearly, so this is clearly non-negative because the logarithm is increasing, okay? And then the second part can be treated thanks to Neumann boundary condition, so the boundary term disappears. And then what you get is just minus gradient of log of AI gradient of AI, which is just minus gradient of AI to the square divided by AI, which is nothing else but the Fisher information associated to each of the species. So what you get is exactly this. Okay. So this is this part is the Fisher information, and this part here is something which is typical of detailed balance. Which I will define a little later in the maybe in order to present things, let's call D, and this is associated to the first example of reaction diffusion, so I will write it in this way, and this is minus dH over dt. Okay. Let's write it this way. So that D is a non-negative quantity, and then it is clear that H is indeed a Lyapunov functional for the system, for the first system. Now if you write instead of, so this is a sort of computation of the global entropy, but it's also interesting to have a computation for the local entropy, the one in which you do not integrate in omega. And if you do this computation, what you will find is the following, that dth, so let's write what it is. So this quantity here. And if you do not integrate over omega, you keep the Laplacian, and you write it in such a way that the term which is inside the Laplacian is the same as this one, except that you have the di which are appearing in the sum. So if you do this, then what you will get here is exactly what you have here, except that you do not have the integration in omega and with the sign minus, so that another way to say that is that this is less than 0. So this is just the local version of the estimate which is here. Okay? Exactly, exactly. So it's something which took us a long time to understand that this was what one should do, actually. Maybe before commenting on the use of those things, let me present the computation for the secant model, because this computation is somewhat different. Of course, there are similarities, but it's not really identical. So for the secant example, so we use the same notations, but now please remember that it goes up to A3, not up to A4. And so if you compute dH over dt, so I will take my paper because I don't want to lose you. This will be the sum from 1 to 3 of log AI dt AI as previously. And so, of course, the diffusion part is strictly the same, except that the sum goes from 1 to 3. So you have this first part, which is the Fisher information. So in some sense, this will appear in any chemical network, because this is really just related to the diffusion. And then the other part is specific to each network. And in that case, what this computation tells you is the following. So we start with A1. So we have minus A1 plus A2 square log A1. The term in for A2 is minus 2A2 square plus A2 A3 plus A1 log A2. And the last one is A1 minus A2 A3 log A3. And one can check that this is indeed, what I put here is indeed what is written here. I hope I made no mistake. Yeah, looks that it's okay. Yeah, that's it. Okay? And now the point is to try to check that those quantities, when you take the sum, it gives you something which is non-positive. So let's say that you always have the Fisher information. which comes out of here. And here you want to put the terms in such a way that something non-positive appears. So the idea here consists in looking at the various terms. If you remember, for each reaction, you have a specific term. So you have A1 is one of them, then A2, A3 is one of them, and A2 square is one of them. So this corresponds actually, it's not really, to be precise, it is the term which corresponds to the complexes which appears in the reactants of all equations. And the idea here is to sort of select each of those terms and try to regroup the logarithms which are related to them. So let's try to do that in an intelligent way. So for example, for A1, let's put minus here. So for A1, you see that you have log A1. Okay, so the one coming out of here. And then you have plus log A2, which is minus log 1 over A2. So this corresponds to putting A2 here. Okay. And in the last one, you have plus A1 log A3. So this is minus A1 log of 1 over A3. So you can write it in this way. Okay. So actually, this is the intelligent thing to do. Then you try to do the same, but you have to be careful. The point is not to try to do it with A2 and A3, but with each complex. So next, you do it for A2 square. Okay. So you put A2 square here in factor, and you try to regroup off the logarithm which are associated. So there is a log of A1. And then you have this minus 2 log of A2. So what it gives is A2 squared divided by A1 once you have put the signs in the right way. Let me check that. That's it. And finally, you look at the third term, the one which is related to A2, A3. And you select the log of A2 and the log of A3, which are here. And you can write it in this way. Okay? Sorry. I'm just checking that I did not do any mistake here. I think it's okay. Okay, so now the trick consists in wanting inside the logarithms only the same complexes as what you have outside the logarithm. So that is A1, A2 square, and A2, A3. So for here it's okay, you have A1 and A2, A3. Here it's okay, you have A2 square and A1. But here you have to write it in such a way that you have those complexes. And as you can see, the only intelligent way to do it is just to multiply above and below by A2. And in this way you have A2, A3 and A2 square. Okay? Actually, if the reason why you have to do something here is that you did a simplification when writing the equations, which would have been actually better not to do when you want to get the entropy structure. Then, let's say, in order to have something which is clearly non-positive, it's better now to add at this level so minus A1 plus A2, A3, like this. Here, minus A2 square plus A1, and here minus A2, A3 plus A2 square. Let me check. That's it. And you can check that I added and subtracted exactly the same quantities. So that's okay. And so now, once you have written it in this way, you can see that you can rewrite it in an abstract way, like minus the Fisher information part, plus the integral. So let me use the standard notation. So this is psi of A1, A2, A3, plus psi of A2, A3, A2 square, plus psi of A2 square, A1, and psi here, sorry, is minus, and psi is a function of two variables, which is defined by x log of x over y minus x plus y, or if you prefer, y times x over y log of x over y minus x over y plus 1. And once it is written in this form, it is completely clear that it is non-negative. Okay. So you end up with, once again, a Lyapunov functional. But as you can see, it's a little more difficult to extract the right quantities from the reaction terms. And this is due to the fact that you do not have such a nice form here, which is really typical of detailed balance. And here, actually, you have a situation in which you do not have a detailed balance equilibrium. And the equilibrium, which is here, is called sometimes complex balance. And so the situation that you have here, let's say, is really typical of complex balanced equilibria. So I think it's maybe, I would like to do two things before the end of this lecture. Yeah, please.
So, in the second case,
Mm-hmm.
at least the way you present it, it looks that you have a very precise equation. You sort of do this ad hoc arrangements, and then you get some precise result. I mean, so now I give you some other network.
Sure. So the
Is there a general rule how to do it?
exactly there is a general rule provided that you have a complex balance equilibrium, which is exactly one of the two things I will try to explain now. But let's say this is something which is not new for mathematicians, in the sense that people doing the ODEs have used that for many, many years. So it's not really something that I invented, or it's something which has been around for many years. And actually, Bao Kwok Tang, which has done some research, some historical research on the subject, even told me that this is more or less already written in Boltzmann works, in some sense. So everything is somehow. So I would not like to give the impression that this is my theory. Let's say this is really something which has been around for many years. Yeah.
So, if you start from a stochastic particle model,
Mm-hmm.
sort of obvious one, right?
Mm-hmm.
Then, of course, the notion of balance is a very simple stochastic
Mm-hmm.
interpretation.
So this I don't know, but I suspect that yes, that you can, in the case of a complex balance equilibria, I suspect that there is a model, a reasonable model for particles, for which you can get easily also the Lyapunov functional. But I'm not completely sure, let's say. I did not check. So actually I want to do two things. The first thing is maybe to explain how we can use the local entropy structure in order to get what was lacking in the theorem, that is the extra integrability. And the second one is to explain maybe briefly, maybe only on examples, what is now a detailed balance equilibrium and what is a complex balance equilibrium. So let me first say a few words about the use of this. Of course, you can do exactly the same in the second example, so I will present it only in the first example. If you start from here, you can see that actually this quantity here is more or less has the same properties as AI in itself. The only difference is that this is not equal to 0, this is just less than 0. And so you need a variant of the duality lemma in order to treat it, which I will write now, but I will not prove it. So variant of duality lemma which tells you the following. If you have omega a good set, and if you suppose that you have now u, which you suppose to be non-negative, such that dtu minus Laplacian of mu u is non-positive, and mu has the same properties as previously. That is, it is bounded between two bounds, so let's say like this. But then actually you have the same estimate as in the standard duality lemma, that is the integral of u square is bounded by a constant times 1 plus the integral of u at time 0 square. And the constant is also polynomially growing. So this is a variant of the lemma of yesterday, in which instead of saying here equals 0, you just say less than 0, but you add that u has to be positive. Okay? So it's a standard variant, which can be proven exactly in the same way. So the proof is almost the same. So thanks to this, you see that actually this quantity here will be in L2. So actually what you get is that AI is not only in L2, but in L2 log L2. And this is the small amount of extra integrability that you need in order to get the weak solutions for any dimension. I will write it, sorry for the. So you get that AI is bounded in L2 log L2 of 0t times omega. And you get the extra integrability. Okay, so this concludes the proof of the existence of weak solutions that we left pending some time ago. And let me now maybe close this lecture of today by explaining a little better what are these different notions of equilibria. In order to do that, I will maybe, what will I keep, actually? A good question. Maybe I will eliminate this part. And I will sort of write again the graphs for the two examples that we selected. So A1 plus A3 gives A2 plus A4, like this. And if you remember, we had two rates for the reaction. And in the second one, which I don't remember at all, so this is A1 gives A2 plus A3. And with K2, we get 2A2. And then we get A1 out of this one, thanks to the reaction with rate K3. So now the notion of complex balance or detailed balance is relative to an equilibrium, not really to a network directly, at least. So let's now pick an equilibrium. Let's say for this one. Then as you can see, what this means is that the concentration of this times the concentration of this should be equal to basically, if I'm not mistaken, K1 divided by K2 times the, or maybe the reverse, times the concentration of this times the concentration of this. Now, if you are in a situation, if you have now a network in which you have reversible equations like this between various parts of the network, and if you have this condition for all the reaction you're looking at, the system is said to be detailed balance. Okay? So detailed balance means basically that the equilibrium that you pick, it has to be an equilibrium for all the reversible reactions that you see in the system. Okay? This is a very strong restriction because it means that first, you have to have reversible reactions everywhere, and then at the same time, the equilibrium that you have picked must satisfy all those constraints. Okay? Now, what complex balance means is the following. That instead of looking at reactions, now you look only at the complexes. So complexes are those quantities that you see here, the ones which are written on the graph. And what you say is the following. If I pick an equilibrium, I will say that it is complex balance if for each complex I'm looking at, basically what is going inside and what is going outside sort of averages in such a way that I have the good equality. So the equalities are written here in that case, okay? And so in some sense, for having a complex balance equilibrium, you just have to check one constraint for each complex instead of one constraint for each equation, for each reversible equation. So complex balance so here it would be detailed balance is an extension of the detailed balanced case. And it's an extension which is very useful in many, many chemical networks. That is, the situation is in which everything is detailed balanced is a situation which is rather uncommon, let's say, in chemical networks. So it's quite important to have this. One has to be careful that now, if you take a general chemical network, you can find equilibria which are not even complex balance. And this is typically the case when you have species which will not go into anything else. So species which only get concentration out of the rest. Or species which only give their concentration to the rest. Those ones, it's clear that they will, for example, for the ones which do not get anything, they will go to zero eventually. Okay? And this is not really compatible with the entropy structure. So in order to be completely clear, for a given equilibrium, it can be nothing, it can be complex balance, or it can be detailed balance. And let's say, sorry, maybe the arrows are maybe confusing. So let's say, if it is detailed balance, then it is complex balance, and then, of course, it is a standard equilibrium, okay? Then the people who have been working, let's say, in elementary graph theory to understand those things, they have discovered the following, that when you have a complex balance equilibrium, and a fortiori when you have a detailed balance one, you can have only one which is in the interior of the domain. So, in that sense, to say that a chemical network is complex balance makes sense. Because in theory, this is something which is related to one equilibrium. But since you have only one equilibrium which is interior, you consider this one and you say that the network itself is complex balance if its interior equilibrium is complex balance. It will be of codimension at least one, let's say. So, except when you start from an equilibrium which is not the interior one, you should converge towards the only interior equilibrium which is existing. Now, this is maybe a theorem now because someone claimed to have proven it a few months ago, but the proof is currently still checked by people, so it's not yet completely sure, let's say. And anyway, the main difficulty is to show that you can really avoid those bad boundary equilibria in the proof. So the whole point is to check really that you will not go toward them. If you are able to show that, then the entropy structure sort of drives you towards the unique interior equilibrium. So just to introduce the lecture of tomorrow, what I will try to show to you is the large time behavior that we can obtain for the two examples that I introduced in the case of PDEs, and as one can expect, it's much easier to do in the detailed balance case than in the complex balance case. And for some reason, which I think has to do with the culture of each subfield, the people in ODE theory, they are really interested in just proving convergence towards the equilibrium, whereas the people who are like me coming from kinetic theory, we have more been interested in showing exponential convergence with explicit rates towards the equilibria. So we have not been really looking exactly at the same quantities, and this can be seen by the fact that in the ODE theory they use a lot the entropy, but they almost never use the entropy dissipation, whereas all what I will present will be really based on the study of the entropy dissipation. Let me conclude by saying that, of course, the examples that we will treat from the point of view of ODEs are almost completely trivial. That is, those have been known for many, many, many years. And what is difficult is to prove that for general chemical networks, you have the expected behavior. Okay, so we do not really, let's say, bring new things for the ODE people. Okay, we just go in another direction in some sense. Okay, I think I will stop now for today.